Start off. It's 10 o'clock, and we got a good topic today and a lot to cover, so we'll get started on time. Thanks for joining our May user group. My name is Wayne Welk, and I'm just going to kick this off real quick before we turn it over to our two guest speakers from Rockwell Automation. Our topic today will be machine safety versus process safety and SIL versus PLE. And this is hopefully going to be a really informative topic. It was suggested, this topic was suggested by David Aldrich, who's also on the call in the background to support us. And kind of instantly knew this was a great topic because it's a common question and I guess a common confusion point for a lot of people. And so we got our two Rockwell experts on today to really help distinguish the differences between machine and process safety. So those panelists will be Justin Ryan. I see Mike has put in some fancy animations for us. Justin Ryan with Rockwell Automation, who is a automation professional and an SIS expert, and Ninja apparently, and Eric Bombere, who is a functional safety engineer for machinery, also with Rockwell Automation. So we'll turn over the presentation to Eric in just a moment and let him introduce himself. But as usual, we like to highlight our upcoming events. And so for Tech Talks, we'll have one more here in the month of May, and that'll be next week, PowerFlex integration with Fisher Rock. And that's going to be a discussion led by Roger McClary, one of our specialists. And it's going to be a good discussion, more of an application discussion, especially around kind of Modbus integration and you know, a solution to integrate to Fisher Rock flow meters. And then we'll come back in June with kind of introduction of the new Stratix 5800 switch. And then Rockwell Automation's integrated service agreements, or ISAs as they're referred to. And then we do have one more user group scheduled. Actually, that should be in June 19th, and it will be on system redundancy best practices. And that'll be a good topic too, because we're going to highlight not just controller redundancy, but we'll kind of look at it at the system as a whole, levels of redundancy. There's so many layers of redundancy that we can do between networking, of course, the controllers, HMI, and even power supply type redundancy. So we'll try to highlight, you know, system level redundancy and best practices. And with that, I'm going to stop sharing and I want to turn it over to our guest speakers and let Eric kind of start the presentation.
Great, thank you. Good morning. You get sharing here, and I think this is it.
Yes, looks like it's about, yep, we got your screen now.
Okay, terrific. Yes, thank you once again, and good morning. I'm Eric Bombere with Rockwell Automation based here in Dallas. I'm a solution consultant focused on machine design and especially machine safety, and increasingly things like what we're now calling mechatronics, so integrating controls with robotics and linear motion in independent cart. So like my peer Justin, we're resources to you for your work in automation and controls. Justin is more focused around process control and process safety, and so we'll kind of give two different sides of this subject together. My beginning subject for the first portion is machine safety. And first, I'd like to introduce a quick PSA I just received this morning. I thought it was timely. I shouldn't say humorous, but I'll go on to the presentation. I somehow was signed up on an OSHA subscriptions, and every day I seem to get a workplace safety reminder. Today it said, you know, being aware of not being caught by machinery. So I thought I'd put that in just for context. But really what we're talking about is machine guarding to keep people safe while they're working around machinery. And I like to include the topic of emergency stop and then things like maybe robotics, as we're increasingly seeing robots deployed in more and more applications in different industries. Initially, it was primarily things like automotive assembly, but now we see robots in place putting things like cookies into a carton, and the exposure and the rates and types of things that people are working around is certainly changing today. So this is kind of the context of our machinery safety. OSHA is pretty clear about the requirement to have guarding. And so OSHA 1910 says we need to have guarding in subpart O. And also related is 1910.147 around lockout, tagout, or the isolation of hazardous energy. So don't let me misstate or misinterpret, think that anything I say today means we don't have to have lockout, tagout, because we certainly do. OSHA is clear about that. The question is, can we carefully and with good engineering practices apply more modern guarding and controls techniques to minimize the use, to require to use lockout, tagout in certain tasks? And then mixed together with this sometimes is the concept of emergency stop. So these are really three things we have to have for machinery: lockout, tagout, guarding, and emergency stop, including things like pull cords, which is really just a long emergency stop function interface. It's not really a safeguard by itself in any means, but an emergency stop implemented. So being as I was told this will be a lot of controls engineers, let's look at the definition of functional safety. And this applies pretty well consistently to both machine safety now and process safety. So this is a formal definition from IEC 61508. This pertains to the equipment under control and electrical, electronic, and programmable electronic safety systems. This is being extended just this year now to also incorporate some non-electrical interfaces such as hydraulics or pneumatics, and I'll get to that at the end of my portion. So what's a more just practical, straightforward definition? What we're saying is we're going to utilize automation to help make sure people are safe. So that's the controls engineer, the functional safety. Some standards that pertain to this, just as an overview or survey, is ISO 13849 Part 1. And this is where performance levels are introduced and described and defined. So we get performance levels A through E from 13849 Part 1. And it has, the rest of it is Part 2, which relates to validation. And validation is a stage of the machine safety lifecycle that after we design it, build it, we're testing it out, and we do terrible things like remove a wire while something is running and make sure it goes to the safe state, or intentionally put a short circuit between two wires on the safety system, and again, make sure it goes to a safe state. So ISO 13849 Part 1 and Part 2 is what pertains to performance levels. Now, 62061, which was just released, a new edition this year, is where we get SIL. So 13849 defines performance levels. 62061 is SIL for machinery. I don't know if that shows up through the screen, but this is where safety integrity levels 1, 2, and 3, there's no SIL 4 for machinery, but safety integrity levels and how to calculate and design to that system for machinery is defined. Now, these are not two conflicting or contradicting standards, really. They've just evolved differently over time, and the efforts are being made to actually make them kind of somewhat merge together or harmonize, which is in process now. And I always like to point out some American standards. So here's an ANSI standard, American National Standard B11.26. This just came out really kind of at the end of 2018. And you can see right here, it's discussing functional safety, and it's relating that back again to 13849 Part 1. So in fact, it's not just for Europe anymore. It's not just IEC and just ISO, but we have ANSI standards that pertain to functional safety. The risk assessment standard, ANSI B11.0, was also just updated last year, as was the B11.19, which pertains to safety design and risk reduction, like light curtains and safety mats, and that was also recently updated in 2019. Now, of course, we have more machine-specific type of standards, such as the Robot Institute, Robotics Industry Association, And that standard has also been updated recently and is very much married or merged with the ISO and European standards. And then, of course, everything we do is governed by some NFPA, certainly NFPA 79 around electrical standards for industrial controls and machinery, and then NFPA 70 being the National Electrical Code, sort of the law of the land. So that's just a quick handful or so of some of the pertinent standards to our topics today. If you have questions about any or all of these or want more in-depth discussion or explanations, please let us know afterwards. From a electrical controls for safety and machinery interlocking, this is a very typical, very simple, not new technology for the most part. This is well established, where we use something like a guard door interlock switch of some type, this one being mechanical, some type of safety logic, and then some type of output, maybe safety rated device to turn a motor off, etc. Schematically, we might implement it something like this. So this is maybe could be up to a 20-year-old design example. And we've got things like dual contacts. So if this wire falls off, our system knows about that and shuts us down to a safe state. Or if this circuit were to weld this contact, we would still have a backup and be able to get into a safe state. Likewise, when this contactor welds shut, we have a backup. So this is redundancy. We'll open up a contactor, still shut off the motor. And because this is a mirrored contact, which is what that funny symbol means, this one's not going to open, or rather it's going to stay open when this is welded shut, and we're not going to be able to reset. So we have a high degree of redundancy, monitoring, diagnostic coverage, different ways to do safety. The question sometimes comes up, well, is this system really safe? And that's not a bad question, but maybe some of the better questions would be, is this safe enough? Is this going to protect somebody while they're doing their job through a controls design? And the engineer's other question we have to ask is it over-designed? Did we really need all this extra stuff and redundancy and checking and wiring? That kind of costs money in the design. And maybe a newer, even better question to consider would be, when we have electromechanical devices like contactors and switches, these things have wear and tear associated over the days and months and years. So we should ask questions maybe like, is it safe enough for long enough? Did we design it to a 20-year lifespan? Or even more recent would be, is it highly likely that this system will work when it's needed, or probability of availability per hour and things like that. So these are more modern approaches to these safety system designs. Here's a more modern system. This has got great stuff like electronics to monitor a door, an emergency stop, using Ethernet with a safety protocol back to our safety rated controller. We've got safe instructions in our PLC code here. Again, safety Ethernet over to some servo drives with safe functionality. And so the question here is kind of the same. Is it safe enough? Did we put enough measures and protections and redundancy into this system? Or maybe did we over-design it, overspent? With electronics, we're not really worried about wear and tear, but we are worried about things like time and temperature and breakdown of semiconductors over the years or decades. So the questions really, again, are, is it safe enough for long enough? And is it available? Is it likelihood that it's going to work when it's needed to keep somebody safe? So that's the modern approach to functional safety and machine design. In context of a life cycle, engineers tend to be practical people, and we want to jump down here and start designing and drawing and picking out devices and working out PLC programming and things like that. But the right place to start is really with a risk assessment, because that's the only way we could really concretely or best determine how much redundancy and extra diagnostic coverage and design we need to put into the safety system. And that assessment will drive out the functional requirements which will then drive our design. And we need to also verify that design, which is to say, calculate with some math, is that design satisfying the requirements that were laid out? And then when we install, we also need to validate it and actually test to see that we're designed for redundancy. We pull out an Ethernet connection, make sure that the system goes to a safe state. So that's the context. I'm not going to go into a deep dive of risk assessment, but just to say the standards all lay out that risk should be measured and assessed and scored as a function of how bad of an injury could occur and what's the probability that that incident might occur. And with machine safety, we're talking about things like bruising and scrapes and maybe a broken bone or a loss of limb or a digit. Those are the severity of harm that we would think about and score to. And the probability might be made up of how frequent and how long is the exposure and how easy to avoid. So a very slow moving machine might have a lower level of risk associated because it's easier for somebody to avoid the hazard. Whereas a fast moving machine, would be likely a higher risk score. And recently we're seeing that this type of scoring method used more frequently. Instead of just kind of a low, medium, high, or a red, yellow, green, or something like that, is actually to put some numeric values in for the machine safety risk assessment. And we might start with things like, again, what type of an injury, so the max loss, if it's a scratch or a bruise, and then all the way down through loss of limb or fatality as a higher factor to multiply. Probability being, how likely or how possible is it to be exposed to that? How frequently as a factor here. And then this also includes number of people. With machine safety, we're most typically worried about one or maybe two people at a time. Some machines, more complex, bigger lines, we might have more people involved. But that's one of the bigger differences of machine safety and process safety. Machine safety, we're thinking about a couple of people, an operator, a maintenance person, quality engineer, whoever is involved temporarily, maybe exposed to that machine, as opposed to process safety, where we're concerned about many people or maybe an entire community and different exposure rates. Okay, so again, as controls engineers, if we're going to use electrical and electronic things, automation, functional safety, then we're responsible to design and verify and validate that system is adequate. So how we do that, we first need to remap our level of controls, safety, integrity, back to our risk. So this is an example of how to do it. This is not the law of the land. This is an example from an ANSI technical report. And it says, we assess first what type of injury, and they define examples, and then the exposure with no guards in place. Kind of think through how often or how frequently, how long is somebody exposed, and then the likelihood to avoid it. So if we said we've got a moderate injury, maybe somebody gets cut, but they can get stitches and they'll be okay later. And we've got a high exposure, meaning, they've got to do that about once an hour or something like that. And it's not really that possible to avoid because, it's going to be in there. We'd say, all right, that's a high risk level. And this technical report also maps that risk level to a design requirement. So if we said from our risk assessment, we've got a high risk level, it says we should design to performance level D, category 3. So it gives us a nice guide. It takes some of the, maybe a little bit of the subjectivity away and tells us how we can go about it. So what that looks like from a category standpoint is we need to decide whether or not we need redundancy or category, how much diagnostics, and then how reliable or highly rated those components in the system need to be. In other words, safety rated devices. And a few other system design criteria as a score for common cause failure. So back to our example of a simple door switch and a relay and a contactor. This might be either category B or probably at least category 1. So there are actually 5 categories: B, 1, 2, 3, and 4. And B means it's basic. I could use standard devices like a limit switch and not safety rated, and maybe a ice cube relay and some type of a solenoid or a motor starter. That would be a category B. If we use safety rated devices, like I showed earlier, then we would have probably at least a category 1 implemented. Category 2 says we need to use some diagnostics or testing. Pulse testing usually is what we're talking about. So something that will be checking the status of contacts and make sure that when they're in a safe state, they worked as they're supposed to. And then something that output of the testing interval to give us some indication or some other means of shutting down the system. Category 3 and 4 are where we actually have redundancy. So we truly have 2 channels or 2 devices with cross-checking. We're checking for open circuits, short circuits. Category 4 has the highest level of testing, meaning we should be able to catch 99% of failures, and preferably when they occur. So we're doing pulse checking, we're checking for cross faults, we're checking each individual contact typically. So that's the category in a quick overview. And to get to performance level, we need to consider which category was chosen, combined with our mean time to dangerous failure, MTTFD, which is a calculation based on the statistical values from those devices in the system. And then we calculate our diagnostic coverage average. In other words, how much % of our failures can we detect and take action about? And then this thing that's called common cause failures, which is system design. And one of the decoder rings for that looks like this. So if we said we need to design to performance level D, and we said we're going to use category 3, we see we can get to performance level D with category 3 as long as we have a high MTTFD, so our mean time to dangerous failure is between 30 and 100 years. And we have even just low diagnostic coverage, which is just 60%. So as long as we can get 60% of our failures captured and diagnosed and taken action on automatically by our safety system, we can pretty readily achieve performance level D with category 3. So that's one method that's in the 13849 standard. There are other methods like a lookup table and some charts, and there's also a software tool called Sistema, S-I-S-T-E-M-A, and those are all means that's a good software tool for determining the performance level. And we need to do that for each safety function in our machine. So in other words, the whole machine is not necessarily PLD or SIL2, but each safety function, such as open a guard door, shut off a servo, press an emergency stop button, shut off a VFD. So each safety function would be assessed and verified by that method. So to wrap up and make the tie between performance level and SIL for machinery, there is a table in 13849 Part 1 that helps kind of correlate and say that, for example, if we are performance level D by 13849, then we're probably SIL 2 by 61508 or 62061, the machine standard. So that's a very typical level of machine safety we see being implemented these days. And then, of course, over here, performance level E, PLE, correlates to SIL 3. And I'm saying correlate, not necessarily exactly, but in general with probabilities of failure per hour, that's how it maps out. Just a comparison of some of the differences between these two standards. Again, we use performance level in 13849, PLA through E. We use safety integrity level, or SIL 1, 2, or 3 in 62061. There's different terminologies for the redundancy, like we call it structure or architecture, category or ABCD, mean time to failure, and probability of failure per hour. So there's some different terminologies, but they essentially accomplish the same end result. How safe is our system for long enough? So I promised I'd mention there's a new version of 62061. I've read through it. We're working on a kind of a more comprehensive presentation to explain some of the impacts of the updates. I'd like to just quickly zoom on a couple of interesting developments. One is there's now methods to extend it to non-electrical technologies like hydraulics and pneumatics. And then I thought this was pretty important input too, or impact, is there's reference around security in our machine safety system. So for the non-electrical technologies, again, there's some examples given with things like solenoids, hydraulics, pneumatics, relays, contactors, etc. So that's now more well addressed in the new 62061 with SIL, as is some detail around security aspects. So we're now responsible to think about things like cybersecurity or accidental changes that might be made during our machine safety lifecycle. And there are other standards that go into detail of how best to do that. So that's my portion. I haven't noticed if Justin is now with us and ready to
should I just request control of your PowerPoint to keep using it, or how do you want to do that?
Whatever you prefer. You can stop and reshare, or you can either request control or just ask me to go on.
Okay, I'm a control freak, so I'm going to ask for it.
Okay, there you go. How'd you know what my screen name was?
All right, thanks, Eric. And if that becomes a problem, Eric, I can always pop it over to my screen. So thanks everybody for coming out. My name is Justin Ryan. I'm a process solution consultant here in the Houston, Texas market. I was just finishing up another WebEx. Had to be a few minutes late jumping over here, so I appreciate Eric starting off for everybody. And as usual, the content was really good. So looking at process safety. Eric, can you flip it back to where the pen is not the, oh, there we go. I got it. There we go. Perfect. Let's take it off. All right. There we go. So starting off with a safety moment. So usually in process safety, we like to start off with a safety moment and cover an incident that's happened to kind of set people's minds on the topic. And this is something that happened 15 years ago in Houston, down in Texas City, and at one of the BP refineries. And this unit is part of the isomerization unit, and used in the refining of gasoline. And when they were controlling it, they had faulty instruments, they had operator training issues, they had a lack of supervision, they had all these issues that came together to cause this incident. It wasn't one incident that caused it. And that's really the point of process safety, is that with process safety, you're really trying to create layers of protection, okay? And they'll even call it, an independent layer of protection. So just to point out, kind of what happened here, they filled this vessel, the column, and they filled it all the way to the top. Of course, it's only supposed to go to a certain level in the middle to where the gas can come off the top. So they filled it all the way up. It then overflowed into a blowdown stack. That blowdown stack was supposed to be replaced 2 decades ago, and they still managed to somehow continue to run it. Engineers 3 times had asked to replace the unit and had been told no. They'd also tried to vent the atmosphere of this, instead of going to atmosphere, to go into the flare, which also would have solved the problem. So there was lots that was done here to try to help not create an incident, and was ignored by management. So in this case, like I said, the personnel was not trained. The HMI didn't adequately show the process information that it was supposed to. The supervisor actually left the site to go deal with a personal issue, and left a junior operator in charge. And one of the interesting ones from the report is that in the 8 years prior to the incident, in the years prior to the incident, 8 serious releases of flammable material from the ISOM stack had occurred. So if you can imagine, you're working in this facility and 8 times you see a geyser come out of the top of this thing. And then at the end of the day, everyone just kind of shrugs their shoulders and says, and then moves on with their life, right? You can imagine that that's not really how we want safety to be dealt with in our world. But if you want to learn more about this, the link at the bottom here is active, and it goes to the Chemical Safety Board. That's a fantastic website where they really review a lot of how chemical accidents occur and what goes on with that. So anyway, just a really good thing for you guys to go look at. All right. So what is process safety? So you had a good overview of machine safety from Eric, and we want to just kind of show where this differs a little bit. So of course, process safety is not about choosing a certified logic solver and calling it a day. It is achieved by following a series of well-defined activities, starting with the identification and quantification of the risk. Okay, so what is the frequency or the likelihood of that risk? And then what is the consequence, or how bad that risk is going to be? Eric showed a kind of a weight chart that gave more weight to things that had a worse consequence. It also gave more weight to things that had a higher frequency, because all of these things go into what our traditional definition of risk is. And so we solve it the same way using these techniques. So this comes from the parent standard of this is IEC 61508. 508 does several things, right? It is what the manufacturers of the safety equipment follow to make a safe piece of equipment. So when they're creating this, 508 defines where that piece of equipment is going to, what requirements it's going to meet, and how it's going to be able to, or what integrity level it's going to achieve. We follow that as a manufacturer, and we utilize that to rate our equipment. Then the users then use the different sector standards to apply those safety standards to their equipment. So for example, 61511 is where the process industry uses to design this equipment. And that has this, what's called the safety life cycle inside of it. And the safety life cycle really drives the user to use systemic work practices that will make sure that this system will last for a long time. So, you know, in a regular control system, it's okay for a maintenance person to go in and make a change, as long as they know what they're doing, and they make a change and they test something and they go, oh, okay, that didn't quite work. Let's try it this way. Let's try it that way. You know, they're allowed some freedom or flexibility there. But in the safety side, if you make a mistake on that safety system, the safety system faults are not always self-revealing. You know, if you miswire a light in your office and you turn on the light switch and of course it doesn't work, that's a self-revealing fault. You immediately know that that doesn't work correctly. But in the safety world, some of these valves might be open for, you know, years and years and years, and never close. So how do you know for sure that that valve is going to shut correctly and that your application code is working correctly if you don't ever have time to cycle it? So 511 really puts in place some life cycle requirements that are unique and different from the BPCS, or the basic process control system, that we want to follow. That also has been made the law of the land via OSHA. So OSHA has a requirement called process safety management. And in 1991, they established 29 CFR 1910, Part 119, and that is called Process Safety Management, or PSM. And they define some hazardous chemicals, hazardous gases that will be the thing that you're protecting against. And just as an example, it says a process which involves a chemical at or above the specified threshold quantities, 10,000 pounds of anhydrous ammonia, 1,500 pounds of hydrogen sulfide, 10,000 pounds of a flammable liquid with a flash point less than 100 degrees in category 1. So they're trying to show what types of flammable materials or what types of hazardous chemicals you have to be aware of. OSHA then was put into place via the Clean Air Act, and it's a part of EPA's risk management plan. A quick note, though, is that even in industries that are not required to follow PSM, they will often look to PSM as a best practice, or what we call RAGAGEP, which is probably the world's longest acronym. So that stands for Recognized and Generally Accepted Good Engineering Practices. So recognized and generally accepted. So if you are going to a court of law and they say, what did you do to try to prevent this accident or this injury? And you say, well, we weren't subject to any requirements from PSM. However, we used those requirements to put in a safety plan. We did a risk analysis. We put in the proper procedures, but we still had an accident. Okay, you're going to more than likely be covered to say that you did the most you could do because you were following RAGAGEP. So that's a good example of where some of the industries are following these practices, even if they're not specifically called on by OSHA to follow those practices. One interesting statement that I like to highlight inside of the document from PSM says, regardless of the industry that uses these highly hazardous chemicals, there is a potential for an accidental release at any time that they are not properly controlled. This in turn creates the possibility of disaster. So again, it's not industry dependent, right? These are all standard ideas behind process control and process safety, so they all apply. All right, so what is this life cycle that we're talking about? Most of the 61511 standard is dedicated to this life cycle. And I have this nice little chart here that shows the life cycle kind of bubbles here. And if you notice on the right, it points out the clause that is relevant to it. And that is the actual clause inside the standard, okay? In 511, they do things like take language that's in 508 and make it a little more industry standard. So for example, in 508, they might use the term called EUC, or equipment under consideration. Sometimes they call it equipment under control, but it's equipment under consideration. But in 511, they would call it more things like the valve or the system or the SIF. They would use some better language right in there, talk about the process risk. So it's trying to make it into language that those users would understand. So the first one that you have is the hazard and risk assessment. So this first box here, right, this is going to be your first step. So you get together a cross-functional team of operations, legal, management, engineering, safety people, right? And you all get into a big room together and you discuss every single SIF, or safety instrumented function, to determine if that is something that needs a SIL requirement on it or not. So what are the hazards? What is the risk? What is the likelihood? What is the consequence? Maybe the consequence is that it'll blow up the entire facility. Well, okay, but what's the likelihood of that happening? Well, it's 0.00001. Okay, well, we're going to put a pretty low SIF on that because that doesn't really matter a whole lot in the day-to-day operations. So, but you go through and you identify all that. Then the next step is you go through and you allocate safety functions to each of those protective layers. So now if we have, so let's say we overfill protection. So we don't want to overfill the tank. So to prevent that, we're going to put a level transmitter in there that's independent from the BPCS. We don't want to have common cause issues. So we're going to put in a level transmitter that's independent of the BPCS, and we're going to use that level transmitter to shut down the incoming valve should there be an overfill event occur or just before, and then we're going to use that. Then we're going to go to the next step and we're going to write an SRS requirement. So a safety requirement specification. So we're going to take that SIF, the overfill protection level controller, and we're going to write requirements around that. What is the voting scheme that it should be in? What is the SIL requirement that it should meet? What is the risk reduction target? What is the, if we're going to have redundancy or not, is it going to be simplex or redundant? So all those requirements go into that document, okay? Then, now this is where a lot of people will try to short circuit this process. They want to jump immediately to the design part, but you have to get through the piece up here at first, which is the analysis part, right? After all of this is done, then you can go in and say, okay, now what tools do I have in the toolbox that will meet the requirement of this specification? Okay. Okay. Is it going to be control logics? Is it going to be guard logics? Is it going to be advanced? Is it going to be trusted? Is it going to be a third party? What is it going to be to meet the requirements as listed in the SRS? So then we put together the system, and then we're going to go ahead and install it, commission and validate it. And we got to make sure that we validate that it does the thing it's supposed to do. Okay. Did I build the thing correctly? And then you also want to ask yourself, did I build the right thing? Okay. If someone says, I want a vehicle that can tow a boat and hold 4 passengers, and then you come up with a Corvette, well, you did build a thing correctly. You built a Corvette correctly, but you didn't build the truck that someone asked for. Okay. So you got to make sure that you build the right thing that was being asked for. All right, so then we get to the operations phase, and this is really where the meat of the life cycle, matters, because let's think about the life cycle of this. You've got people that are working on this job for, let's say, a year, maybe 2 years at the tops, at the max, trying to design the system, but now it's going to be in operation for 20, 30 years. So is it more likely that you're going to make some kind of systemic mistake early on when all the, sorry about the coughing there. My allergies are going insane. So sorry about the coughing in the audio. But you've got 20 years now of people running this equipment. And so there's a high likelihood that they're going to make some kind of mistake down the road by an improper swap out. Maybe they have lines get crossed and they don't realize that now there's a common cause failure. So all these different things that come into play. So you want to follow the safety life cycle and make sure that any changes that are made, you go back now. So notice this line. So you want to go back here all the way to the hazard and risk assessment and say, okay, the hazard and risk assessment assumed that information A, B, and C were correct. Well, maybe you just changed B, okay? And so now B is no longer an adequate assumption. So now you have to go back in here into this loop and change that because it's now an inaccurate assumption and is not valid. So that is definitely where we want to go through and do that, okay? And then of course there's a loop over here for when you finally want to decommission it. Does taking out, for example, this temperature transmitter or this level transmitter, does removing that now make a hazard somewhere else because another SIF was assuming that that SIF was in place? So, you might have said, well, we don't have to worry about level control because we've got this other thing over here that'll prevent it. And then suddenly 10 years later, because you don't need it anymore, you decommission that. And now you have to go, oh, well, hang on. That was used in the assumption of this SIF over here. And so now we have potentially a problem. So you have to go look at that. So what I wanted to try to really drive through with you guys is that the life cycle drives the behavior. It drives that systemic behavior to make sure that we follow the life cycle and don't do things that compromise safety. There are literally books and books and books on how people have broken the system and caused accidents. There was one of the major ones. I mean, just that incident I talked about with Texas City, right? There was at least 6 or 7 different causes that all happened at the same time to cause that incident. It wasn't one single thing. So it really is a systemic problem that has to be looked at. So then there's other sector standards that are out there like NFPA, the National Fire Protection Association. We've heard about those for boilers and fired appliances. Then there's also API, the American Petroleum Institute. they have a whole set of standards as well on design and how to use safety systems to control those appliances, those systems correctly. All right, so a quick look at layers of protection. So when we build our layers of protection, we have first a preventative layers and then our mitigative layers on top. So preventative means we want to keep the thing in the pipe, right? We don't want to let that out of the pipe. We want to keep it in the pipe. And so what do we need to do to prevent that? Well, the basic process control system is going to be the first thing that starts that. Its job is to keep it in control. Then if that can't happen, now we have an alarm layer. So that alarm is going to trigger and to notify the operator, hey, the process is out of control. You need to take an action to do something. An alarm is supposed to be an actionable item, right? It's not supposed to be something that's just sort of informative. It's supposed to be actionable. You also have to make sure, by the way, that on an alarm, the way the standard is written, you need to give that operator roughly 20 minutes to be able to respond. If the operator does not have more than 20 minutes or more to respond to that incident, you typically are not allowed to take credit for that. Because, what if the operator's having lunch and just misses it? Or what if the operator had to take a personal phone call or use the facilities or, whatever can happen to somebody on their normal work day? Or maybe it takes 10 minutes to figure out what on earth is wrong. So you got to make sure that there's actually adequate time for the operator to intervene before you can take credit as a layer of protection. So now that doesn't work because maybe the valve isn't working or it's not tuned properly. So now the SIS has to come in and take action. So again, this is why the SIS must be an independent layer. Try not to use the same source of instrument error. Try not to use the same source of power. Try not to use the same, even if you can use diverse valve types, things like that. So there's ways you can try to really reduce the common cause issue. Let's say you picked the same kind of valve for everything in the system, and then you went and used a different chemical that had a caustic effect on that valve body, and it froze the valves. Well, if your safety system had the exact same valve as the process system, and it froze as well, well, now you've just, with one action, you've taken out two different layers of protection at one time. So that's why it really needs to be independent and diverse. Now, if that can't stop it, now we get into, what are our active protection layers? So things like rupture disc, relief valves, right? Things that are going to mechanically actuate to try to now one sort of last ditch effort to keep this thing under control. You are going to vent some stuff to atmosphere, but it's certainly not as big of a hazard as if you would let the entire thing rupture. This is also where, for example, like a flare might come into play, okay? Now we've had the incident, we were no longer able to prevent it. So now how do we mitigate it? So now we have some passive protection layers here, like a dike around the tank. Maybe we've got some containment where we have the operators in an explosion-proof control room so that they're not injured by the explosion. And so I don't have loss of life. I certainly have loss of equipment, loss of assets, but I don't have loss of life. And then lastly, we'd have like an on-site fire department. We might have an emergency response that goes into place. We might have shelter in place, or we might have evacuate, depending on the types of chemicals or gases that are released. So these are all part of that equation. So now, as I'm now identifying these risks and these hazards, okay, there's going to be kind of an initial risk that is inherent in the system. So this would be the risk that is there with no mitigations in place, no safeguards. So what would be the sum total of that risk, all right, which is both the consequence and the frequency of that. Now, where we want to get to is the tolerable risk. So tolerable risk says, okay, I can operate this at this risk and know that my people are safe enough, okay? Of course, obviously, some industries have a higher tolerable risk because the thing they do is dangerous. But even driving your car to work has a tolerable risk. Your car, there are several thousands of people that die every single year in Texas on the roadways. So it is false to say that driving has zero risk. However, it is a low enough risk that you feel comfortable getting in your car and driving to work every day, and you feel that it's tolerable. So how do we go from the inherent risk to the tolerable risk? Well, we start to now put in our different mitigation levers. So the mechanical things we talked about, right? The dikes, the flares, the relief valves, the basic process control system has a mitigative effect. The alarm, so as long as we have enough time, we can say that the alarm is also another layer of defense against going out of control. And then whatever's left over becomes the SIS, okay? So that the further risk reduction down to or below the tolerable risk level is the job of the SIS, okay? And so that leaves us at the residual risk level now. So what is the residual risk that is left over after all these things are put into place? Now, what's important here is the size of that arrow is kind of what matters. And so if I look at the size of that arrow, that ends up becoming my SIL. So I have my safety integrity level. We also now can look at the inverse of the probability of that and come up with a term called risk reduction factor. We usually talk in terms of risk reduction factor because it's a lot easier for humans if I told you I had a risk reduction factor of 500, it would be obvious to you that if I said now I have a risk reduction of 2,000, that would be better, right? That would be a larger risk reduction. But if I start talking to you in terms of 3.2 times 10 to the negative 5 or 1.6 times 10 to the negative 6, it kind of takes you a second for your brain to tick over into scientific notation mode and figure out which one's better. Okay, so we usually take the inverse of that and we get risk reduction factor because it's a much easier way to talk about it. So as I look at these different sizes of these arrows, the size of the arrow is the risk reduction. Okay, so if you have worked your way down to close to the tolerable risk level, but you're not quite there, the gap that's remaining is the amount of safety integrity level that you need to apply or the risk reduction that you need to apply. So that's where the SIL terms come from, right? So SIL 1, SIL 2, SIL 3 are really just orders of magnitude difference. So if I said putting this in place is going to take this event from a once per year to a once per every 10 years, well, that would be considered a decade, right? Or an order of magnitude reduction in that risk. And so that would be the case then for me putting in an SIS. So maybe you say, I only want an injury. Well, none of us want it, but I only want to accept an injured employee once every 10,000 years. Well, if you've done the math and now you're down to once every 1,000 years, well, you need another order of magnitude to get it down to 10,000. So you would put in something that had at least a risk reduction factor of 10. And that risk reduction factor of 10 would take it to a 1 in 10,000. And now you can say, okay, now we have an acceptable risk for our employees to work around this environment. And don't forget too, that risk in the process safety world, risk can be associated with people protection. It can be associated with asset protection, actually protecting the piece of equipment, because obviously it's very expensive. Protecting the environment. So not spilling, oil into the Gulf of Mexico, right? That can be a risk that we calculate. And then lastly, even your public perception. So how does the public perceive your company? If they perceive your company negatively, maybe you don't get the investors that you need. Maybe you don't get the employees that you need, right? So safety and those targets can really be something that is quite open and broad. So this is our portfolio to accomplish process safety. We can use the guard family as long as a simplex de-energized to trip or fail-safe system is acceptable for use. We do use these in some process safety applications. If you need analog safety, you have to use the Point.io family or the soon-to-be delivered analog safety coming with the Flex 5000 platform around the August timeframe, or maybe October timeframe, excuse me. Control logics can be used with the 1715 IO to deliver a SIL 2 up to a SIL 2 capability in there. And then of course we have through our partner Sensia, you have the advanced and trusted systems that can be delivered there. So Eric, you want to grab the last part there?
Certainly, happy to. Just want to point out a landing page and some great tools and resources we have. So these are a combination of machine safety and process safety. We have about 200 documents that all start with publication safety-AT. And these include wiring examples. They include a discussion of the safety level that's achieved. There's also ladder logic files, if it's a guard logic, IO configuration, and sustainment and validation. So the address is machinesafetysolutions.com. But as I mentioned, there's other process and even electrical related safety things. So some of the newer documents, if you download the PDF and you open it up in a PDF viewer like Adobe, on the left side, there's a paperclip. And under that paperclip, then there's actual file attachments with that PDF. So you download the PDF, it seems like it's tremendously huge file, but that's because it has other files attached to it, including AutoCAD, ePlan, Logix file, system for verification, and then an example validation checklist to go through and do the things in that system to see that it's actually working right. So that's the website. There's actually a wealth of stuff that's on there, not just machine safety, but process safety related topics, safety management. That would be something to go and discuss with maybe your company's operations and finance and EHS management and things like that. And then also some things around electrical safety, arc flash reduction and things like that. So very rich place of resources. You also have access to lots of people within Reynolds and Rockwell to support your efforts. Most of these things are free guidance for our customers, and we also have safety consultants and engineers that are available for projects or consulting on a kind of per hire basis. So again, lots of resources available to you. If you have any questions or you want some one-on-one meetings, please again reach out and let us know. We're happy to help. So that takes us right about to our scheduled time. It doesn't allow a lot of time for questions, but were there any questions in the queue or anybody want to voice one or ask for some detail or follow-up, please do.
Thanks, Eric. Thanks, Justin. Yeah, if you want to type in a question in the chat or raise your hand, we can unmute your line. We'll give everybody a few moments to perhaps type something in.
There's also, I will say, while folks are typing, there's also a document called the process safe book. So I can probably sneak it in here on the chat real quick while we're talking. But the process safe book, if you would like more information about 61511 and how that works and maybe how all that goes together, Rockwell has a document called the process safe book, and it is a great kind of vendor neutral guide to that. So it's something that is definitely worthwhile. If you ever need to explain to your management why you have to do something, that is a good guide for that, because it kind of explains the safety standard independent of Rockwell. So I just put it in the chat there.
Okay, thanks, Justin. Looks like I haven't seen any questions come in, so we can go ahead and conclude our session. Once again, we want to thank our guest speakers, Eric and Justin, for an excellent presentation. It lived up to the hype, and Justin, you lived up to your ninja status that Mike had dubbed you there as well. This session was recorded, so yeah, if you wanted to view it again, or if you have some colleagues that perhaps couldn't attend and like to share, we'll have that available to watch later as well. So thanks again, everyone, for attending, and thank you again, Eric and Justin. We'll wrap it up.
Thanks all.
Great, thank you. Have a good and safe day.